Okay, so welcome back to DSP. And today, we will continue from last week. Last week, we have started our discussion on a kind of system, linear and time invariant. And we have introduced that these are actually two concepts. Linear is one concept, time invariant is the second concept. So when the system is both linear and time invariant, we say the system is LTI, linear time invariant. Okay, linear time invariant. And we also introduced that there's a crucial concept, an important concept for linear and time invariant system in that all that matters is its impulse response. We care about for such kind of system, we care about its impulse response. Namely, if the system is just denoted by the letter H, so that we have the input X, and the output is denoted by Y, where we write Yn equals to the system's the output that the system produces. The system produces an output. Okay, that's our notation. And what is impulse response? Impulse response is defined as the system's response to delta function. So we say h of n is defined as the output that the system produces when it receives the delta function as its input. Okay, this is our definition of the impulse response. Now, and last time we also mentioned, toward the end we mentioned this. We mentioned that for a linear and time invariant system, we know that if the delta function produces this output, then for any arbitrary other input, for any arbitrary 任意的 any arbitrary other input, the system produces the system produces an output that can be written as summation xk h of n minus k, where we sum up over all possible k. And this, as you may notice, that this is a convolution of two sequences, right? This is exactly equal to convolution of x with h. And I've emphasized that the result of convolution is also a sequence in time, which is our output. So that's what we have. We were at last time. Okay, so today we will continue from here. We'll officially introduce Z transform. So the idea is that when we have any signal in time, after the Z transform, the corresponding function is defined on the complex plane. You can see that here, Z. What is Z? Z is basically somewhere on the complex plane. Okay? And then we'll talk about that when we write this down, there's a matter of convergence. Sometimes when we write down the Z transform, turns out that it has an expression for sure. 有个什么表达式哈. But some expressions do not converge everywhere. Okay? In general, so there we need to talk about a region of convergence. Where on the complex plane can we actually calculate, can we define the Z transform for any arbitrary given sequence? Okay? So there's an issue of convergence right here. Then mainly I want to move on to a special kind of linear and time invariant system. Okay, so we'll talk about linear and time invariant systems that are defined according to difference equations. Difference equations. Difference equations. Okay. In Chinese, difference equation is 差分方程, 差分方程. So this is probably the most important concept you want to master in this semester, because DSP is all about using the difference equations to process our signal. I can very confidently tell you, we play with difference equations. Okay, so today we'll officially introduce difference equations in the context of signal processing. You'll see that how we can use the equation to process an input and produce an output. Okay, so there are examples, and we'll define the impulse response to such kind of systems can be written as. Turns out that the impulse response, the impulse response is denoted by small h, right? Small h, and then big H is its Z transform. And we'll see that in general, when we are given a difference equation, then that gives us a system whose impulse response H after Z transform can be written as the ratio between two polynomials, BZ and AZ. Okay? And from there, we can do a lot of things. We can discuss frequency response. We can discuss impulse response. We can calculate, we can write down a closed form expression for the impulse response using inverse Z transform, going back to the time domain. And then for certain reasons, let me tell you the result. For stable systems, then we can talk about frequency responses. Okay? So if a system happens to be stable, then when the system receives a signal at a certain frequency, we can talk about the gain. We can talk about the phase shift. Okay? Frequency response and impulse response, stability. So these are the kind of topics that we will go through today. Okay? And so so far so good. Shall we start? Yeah. Okay, so to begin, let's see where what we had last time. Okay, last time we talked about linearity as well as time invariance as two properties. Linearity means that when we linearly combine the input, the output also linearly combines. Okay, and time invariance that when we delay our signal by m samples, then the output is also delayed by m samples. The system's behavior stays pretty much the same now or after or later. So this is the property that we call invariant against time, or time invariance. And the important property right here is that if a system is both linear and time invariant, that is to say, for any LTI system, then the output that the system produces can be written as the output that the system produces can be written as, we can prove it actually. So by our derivation last time, we showed that the output is going to be calculated by convolving the input with the impulse response, and the impulse response is defined as the output that the system produces when it receives delta function as its input. Okay, impulse response convolution. So all you need to know, all you need is impulse response, and we also say that in the textbook, it says the impulse response completely characterizes the system. In this case, complete characterization. Because now we can calculate the output signal for any arbitrary input. Okay? The output is just simply can be calculated by convolution, by convolving our input with the impulse response. So far, so good? Okay. That's what we had last time. So this time, let's move on and talk about Z transform. So here is the definition. Z transform is the result is a function of Z. Okay, the result is a function of Z where Z is on the complex plane. Okay? D is on the complex plane. And the definition you see is a summation over all possible n. Let's say n, when I don't write the range, in the most general case, n goes from -infinity to infinity, right? So sum over all n, but then we multiply our signal with z to the -nth power, or that is to say z inverse. The inverse means 导数, 1 over z. I say z inverse, 1 over z. 1 divided by z, yeah. So z inverse to the nth power, okay? Yeah, I often call it z inverse. Z inverse. Inverse in Chinese means 导数. 1 over z, basically. 1 over z is called z inverse, right? So yeah, this is a pretty simple definition. The way it looks, this pretty simple definition. But we need to add a kind of, be careful. We say xz can be defined as this infinite sum only if the sum converges, right? If the sum converges. If this summation, this infinite sum converges. Or we simply say if x, if the summation converges. Okay, now we'll come back to convergence. There are ways to, especially after we talk about difference equation. But keep in mind for now that when we write down this expression, an infinite sum, you can expect that in the most general case, maybe in certain regions on the complex plane, the summation simply does not converge, and it's not defined. So we say, in that case, we say x of z cannot be defined over that region. Okay? So it's possible that in certain region, this summation converges, but in other regions, this summation does not converge. Okay? But if the summation converges, then there's an important property which we also call convolution theorem. So that is say, if x and h convolve in time, when we have the convolution that happens in time, and we know that in the context of LTI system, when we have an input and the impulse response and they convolve to produce the output, right? So it turns out that in the Z domain, the transform multiplies. Their transforms multiply with each other. Okay? So to write it down, this is a well-known fact that if y equals to x convolve with h, then y of z going to the Z domain, after the transform, yz simply equal to xz multiplied with h of z. Okay, and we can simply check it. Let's try to check it. Right. So y of z, and this is also a convolution theorem. Okay. So how do we check whether this is true? Again, summation, by definition, y of n is x convolve with h, right? So y of n is summation over k, x n minus k, hk. That's y of n. Okay? and then we put z inverse to the nth power to the outside. And just now, just routinely, when we see two summations, what do we do? When we see two summations, let's try to change the order and move k to the outside. And anything that does not depend on n should be kept outside, right? hk. Then n, summation xn minus k z to the minus nth power, okay? And this summation goes, is indexed by n. So far so good. And there's also a shift theorem here, okay? It should be pretty obvious but because of the way the transform is defined, okay? X of n minus k. Now we have, in this step, we are going to use the property that x n minus k. That means the signal is delayed by k samples. Okay? When when the signal is delayed by k samples, the corresponding z transform. Now we have a factor of z to the minus k in the front, and then x of z. Okay, that's a shift theorem, a property which you can easily check. Yeah, this is true. So then now let's try to substitute this in here. Then what we have, it becomes summation k, hk, and what do we have? Z to the minus k and xz right here, right? Okay, so we're going to finish pretty fast. And now you can see we have a factor that does not depend on k, right? This factor does not depend on k, so it can be moved to the outside, and the inside, what we have, what's remained there, becomes hk d to the minus k. And what is this? This is exactly the z transform of h. Okay, so this now we have completed our derivation. Indeed, we've shown that when we convolve two signals in time in the z domain, the z transform multiply with each other. Okay? So that's a convolution theorem for z transform. Okay? So far, so good? So that's the idea. But keep in mind that we can have this discussion only over a region when both x of z and h of z exists. Yeah, so seriously, think about this. When we have a signal x and a signal h, and then, of course, they can always convolve in time. Yeah, convolution in time is always well defined. Okay? But when we go to z domain, this convolution theorem holds only in a region where both x of z and h of z converges. Okay, so yeah, so maybe we should add a remark. Okay, over a region, this equality holds over a region where both x of z and h of z and h of z, both of them exist, okay, then we can rigorously talk about equality. You know? Otherwise, the equation does not make any sense. Okay? Yeah. All right, so that's kind of a remark I would like to suggest to you. Pay attention to the issue of convergence. Right. All right, so in the next few minutes, I'd like to invite you to think about this, about the convergence issue. Okay, so let's say we have an arbitrary signal x. Okay, so how do we identify the region of convergence when we take it to the z domain? Okay, when we attempt to transform our signal x of n to the z domain. So what general properties do we have? What are the different situations or cases of the region of convergence in the z domain? Okay? So to enable this discussion, it turns out that it's convenient to talk about t greater than 0 versus t smaller than 0. Okay, after time 0, on time 0, or after or before time 0. Okay, so I'm going to suggest that now we introduce some kind of notation, useful notation. So here, we are going to define that this x plus, the plus part, and there's the minus part. And the plus or minus indicates whether we are talking about positive time or negative time. Okay? So what exactly is this? We define x plus of n. We define x plus of n as, maybe I should change the highlight. Okay? We define x plus of n as simply xn for time 0 or afterward. Okay? Time 0 or afterward. And this and is 0 for any time before 0, before time 0. And similarly, just in an opposite manner, we define x superscript minus n as that, such that it equals to x of n before time 0 and is 0 afterward. Okay? So it should be pretty clear that xn equals to x plus x minus, the sum of the two. Because one is defined strictly from time 0 and later, right? And the other is defined strictly before time 0. So that's basically the right-hand side part and the left-hand side part with the boundary of time equals to 0. So we put the right-hand side part and denote it as x plus, and the left-hand side part, we denote it as x minus. Okay? And of course, x equals to the plus part plus the minus part. Is that clear? So that is to say, let me actually just write it down. This part is x plus. And this other part before time 0, this is time 0, okay? Time 0 right here. So before this part, that's x minus of n. Oh, not minus 1, minus, just minus, not minus 1. That's just our notation, okay? All the samples before time 0, collectively, we call it x minus. And otherwise, the other part is called x plus of n. Okay? So simply just to break our signal into two parts, the plus part and the minus part. Okay? And of course, we have x of n equals to the plus part plus the minus part. That's all the samples. And when we take the z transform, then sure, x plus may correspond to a z transform, and x minus corresponds to its z transform. Okay? Z transform is a linear transformation. And then we can continue to attempt to write it down. Yeah? X plus of z. What is x plus of z? It equals to sum over all n. But x plus of n is 0 for time before time 0, right? So the summation now goes from 0 to positive infinity. Okay? Whereas, what about the other part? The other part, because x minus is 0 for after time 0, right? So the summation should go from -1 to minus infinity. Yeah, just in the negative time range. Okay? So that's why we change, by changing the summation index, we have this expression. Okay? And then here, I didn't change anything, but in here, I'm making a change of variable. So what change did I make? Can anybody tell me what change did I make? I define a new summation index, right? So here, maybe it's clearer that here, if we define m, I should say m prime is defined. We define this, when we define this change of variable, then this is actually m prime m prime, a dummy variable, so it's not really important, okay? Yeah. All right, so what do we have? So now we have two power series. Turns out that now we have two power series. This thing, the power series, two power series, okay? How do I explain? So this thing is a power series of Z inverse, okay? And this other half, the negative time, corresponding to a power series of Z. Yeah. So for those of you that kind of forgot about what's the definition of power series, okay? So the power series, so let's spend some time to review this idea of power series, okay? So power series means that when we have a sequence counting from n index 0, okay? So when we have a sequence and its first term is A0, second term is A1, third term A2, and so on. When we have a sequence starting with time A0, okay? A0, A1, A2, and the sequence may go infinitely. 可能是一个无穷数列, or the sequence may go infinitely. Okay? So for any given such kind of infinite sequence, then we can define a function. We can attempt to construct a function. We can construct a function. Just by construction, we can attempt to write down this expression, fz equal to the summation of an times z to the nth power. And this is called the power series. And this sequence is called, I should say the power series corresponding to the sequence. I mean, this function, did I say sequence? This function f of z, when we write it down in this way, f of z is called the power series corresponding to the sequence a of n. To this sequence a of n, where n is from 0 to generally the summation, the sequence can have infinitely many terms. 有可能有无穷多项啊。And now next I want to just tell you a fact. For any power series, when we attempt to write down an expression like that, when we write down an expression like this, then the region for fz to converge has only three possible cases. Only three cases. Okay? Case number one, we're lucky, the sequence converges everywhere on this complex plane. It's possible. Okay? It's possible that the sequence may converge everywhere on the plane, over the entire complex plane. Okay? So that's one possibility. So that's one possibility. It's possible, yeah. The first case that we are super lucky for a given a of n, it turns out that this f of z, when we write it down, it converges over the entire complex plane. That is, whatever z we plug in. In that case, for whatever z we plug in, the sequence is always well-defined. The sequence converges. That's kind of the most lucky case. Okay? It's possible. For certain sequences, this is possible. Okay? So case number one, the sequence, the series, the summation can converge over the entire complex plane. It is possible. Okay? Case number one. And case number two is quite rare. Yeah? It's possible that, unfortunately, it converges only at z equals to 0. This is funny. Over the entire plane, this sequence converges only at the origin. Okay, that is to say, even if we move z slightly off the origin, just by a tiny little bit, wow, the sequence explodes. It does not converge. It is also possible. It is also possible to have such a situation, okay, theoretically. But the most general case, most common case is that neither 1 or 2 is true. But the third case is also funny. So now the third case is worth some explanation. The third case is the only otherwise. I mean, if neither 1 or 2 hold, then the third one must be true. Okay, so let me tell you what is the third case. The third case is that begin with the existence. Then for the third case, there exists a radius, where r stands for radius. There exists a radius, a finite radius, radius 半径. There exists a finite radius, such that what? Such that f of z defined as this summation converges over the region of z within this radius, okay, on the complex plane. But it might be helpful to draw a complex plane, okay? So the complex plane has the real part and imaginary part. So we are saying that there exists a radius. There exists a radius of r. There exists a radius of r, such that the power series converges inside the circle of radius r. And diverges outside the circle. Okay? That's the only possibility, third case. Okay? If the power series does not converge over the entire plane, and we are not so unlucky, that's so unfortunate that it only converges at z equals to 0. So anywhere in between, the third case that tells you this mathematical theorem tells us that there exists a radius. So we can, from that radius, we define a circle. We define a circle of that radius, and it turns out that we can identify such a circle, such one circle. Such one circle so that the series converges inside and diverges outside. Okay. And let me finish writing. And diverges outside. Okay, I think this is kind of a simple result, but it's worth paying some more attention to this. This is kind of funny, okay? I think it's funny in two ways. Please, finish writing. But I'd like to share with you that I found this theorem funny in two ways. Surprisingly interesting in two ways. First is the theorem. First funny thing is that the theorem does not tell us what happened right on the circle. It tells us that inside the series converges and outside diverges. So it does not and cannot tell us, guarantee what will happen right on that circle with r. So funny things, okay? So I have two funny observations, funny remarks. Funny one, for z exactly on the circle, there's no conclusion, okay? There's no conclusion, no theorem whatsoever. Okay? So I find this funny, okay? That's the first funny thing I noticed, okay? But does anybody have a comment? Want to guess what I found? The other funny thing. What is the other funny thing I found from this theorem? Maybe I should say funny, because I should say this theorem is pretty powerful. Yeah. If you think about it, okay, the first case is converging over the entire plane. The second place is converging only at the origin, right? But the third case, really, it tells us the region of convergence is always a circle. Right? And I think that's funny. Out of any possible A of n, any possible sequence A of n, so the region of convergence can never be a square or a triangle or any other shape. The region of convergence is always a circle, centered on on the center at the origin. Okay? This region of convergence can never be anything other than a circle. And I found that surprising. To me, that's quite interesting. Okay? So at least to me, okay? To me, the region of convergence cannot be a triangle, cannot be a rectangle, cannot be a 八字形 or a heart or 蔡依林 the heart or anything. Okay? So it's always a circle. Okay? Yeah. So it's always a circle, and I found it funny. Okay? I really found it funny. Yeah. What is this? Dude, what is this doing to me? Modifications are not in sync. Which version to keep? The late version, okay? Yeah. Right. Regional convergence is always a circle. Surprisingly, okay? So for those of you that have taken the course PDE and complex variables, in the textbook there should be a proof. Yeah. It turned out that this is not that hard to prove, but the result is pretty strong. The region convergence is always a circle, and the center of that circle is at the origin. It cannot be anything else, right? Okay, but with this nice property, then we talk about the power series. The power series correspond to a sequence and which start with the term A0, A1, and A2, and so on. So for any such sequence, we can define a function, and the function is well defined either over the entire plane or only at z equals to 0, or there's a region of convergence, which is always a circle. There exists a radius, okay? And the radius serves as a boundary, so that inside that radius, the series converges, and outside it diverges. Okay? So what are we going to do with this nice piece of knowledge? Okay, this is now your knowledge. Okay, so now let's go back to our construction of x of z. So now we have an expression. Now consider again. Now consider again that Consider again that x of z for our signal can be written as a summation of two parts. One is the positive part, the other is the negative part. Okay? And both of them now can be regarded as a power series. For sure, this is a power series, right? Because here we have z to the n power. And it's just that the coefficients are x of minus n, okay? But this is certainly a power series of z. But this thing here, we say it's a power series of z inverse, okay? Because now what's inside here is 1 over z, okay? So this thing just it should be clear that this summation defines the power series of z inverse, okay? And that's that, and yeah. Let me finish writing. The positive part of the signal corresponds to a power series of z inverse, and the negative part corresponds to a power series of z, simply a power series of z. Okay? So therefore, in the most common case, we should say exist an R1 such that the power series converges inside such that the power series converges in what? Now let's apply the theorem. Exist R1 such that the power series converges in 1 over z smaller than R1 and diverges outside. Okay. And similarly for this part, because it's a power series of z, now we know that exists R2 such that, let's practice, so that n from 1 to infinity x minus n z n converges, or simply say exists, in what? In z, inside the circle. Okay, so now our z transform is broken into two parts, and we expect that one part converges inside a circle, and the other part, I'm saying that one part converges, this part converges inside a circle, and that other part converges actually outside a circle, to the outside, not inside. Why? Because here we have a power series not of z, but of z inverse, right? So therefore, the region of convergence we expect to be outside this R1, okay? Let me just simply say in other words, okay? In other words, outside that circle. So that's a general combination. The general combination, okay? The general combination is that we expect when we write down for any arbitrary signal in time, I mean really arbitrarily any signal in time, okay? We expect that when we attempt to write down the z transform, the region of convergence should be outside one circle and inside another circle, okay? So in the most general case, now, let me just summarize. So then we have case one. The case one is that sure, the one small circle is smaller. One circle is smaller than the other circle, so these two regions have overlap. They have intersection. They intersect. 有交集啊。Outside the first circle and inside of the other circle, when the two regions overlap, when the two regions have intersections, then that's case one. So case one is that, sure, which one is smaller? Case one is when R1 is smaller than R2, and we're good, okay? Okay. So case one is when R1 is smaller than R2, then our region of convergence should be the intersection. Now, outside the first circle and inside the other circle, okay? That's one situation. And case two is possible that R2 is actually infinity, okay? It's possible actually the second sequence converges everywhere. It is possible, right? Then in that case, the region of convergence, is simply outside the first circle. Simply outside the first circle. And we say this is a region. This is a subset that's inside the complex plane. That's contained in a subset, a subregion of the entire complex plane. Okay? That's case number 2. And case number 3 is also possible that the two regions do not overlap. Okay? Case number 3 is that we are sorry is when Case number 3 is when R1 is greater than R2. Okay? When R1 is greater than R2, then the two regions do not overlap. Then we say the region of convergence is empty set. The plus part may converge over outside the circle, whereas the minus part converges inside the circle. But if you are so unfortunate that the first circle is larger than the second circle, then they don't overlap. The outside of the larger circle and the inside of the smaller circle do not overlap. Okay, that's also possible. Okay, that's also possible. Okay. All right. And there is probably also the fourth case where, when R1 is 0, or what? There's also, please tell me if you think there's a fifth case, okay? But case number 4 is when if R1 is 0, sure, then the region of convergence is inside the circle, except at the origin. Okay? That's also possible, All right. Okay, so seriously, let me know if you find there's a fifth case, okay? So please tell me. But otherwise, it's always a combination. It's a matter of whether the two circles, the outside of a small circle and the inside of a larger circle, you know what I mean, Two circles, and you consider if the outside one and the inside of the other overlap, okay, Okay, so all these cases, turns out that in most of this semester, we are, at least in my classroom, okay? In my classroom, I'm most interested in case number 2. Turns out that for the kind of system that we will encounter, turns out that for the kind of system that we encounter, mostly we talk about case number 2. And I'll tell you why. Okay, later I'll tell you why. Okay, but here I just want to point out that case number 2 is the case that interests us the most. Okay, we're most interested in case number 2, where the region of convergence for Z transform is outside that smaller circle. Okay, I'll come back to that. But before I think then. Question? Okay. So let's take a break of till 20 minutes after 2, okay, 2:20. And when we come back, we talk about frequency response. Right,对，等一下会介绍这个，一定会介绍
为什么这里看过去不是大鱼？
sorry， 我写错，对不对？对，我写错，好，我马上更正，好， 可以帮我准备一杯水吗？ Hello. All right. Okay, so yeah. So let's come back to. I have a correction, I think, for this our fellow student sitting right there. Okay. Thank you for pointing out an error that I made. Okay. So now you see, in our discussions, we have the power series and it converges. Each power series has a regional convergence. So in this case, because it's power series of Z inverse, so the region of convergence should be Z inverse smaller than R1. So that, in other words, we should write down Z greater than Z. Sorry. 哎，这个 button 错，哎，我一直按错。那个麦克风长得太像这个了。The two icons look too similar. I should complain. Yeah. All right, well, let's take it easy. All right. I was saying that 1 over Z inside R1, okay? In other words, Z should be outside 1 over R1, not R1. So let's make a correction right here, okay? The radius there should be 1 over R1 if I write it down here as R1, okay? So that's a mistake I made. Thanks for the correction. And then, so it's just for the convenience, let's call it row 1, okay? Let's call 1 over R1, but let's call it row 1, row, the Greek letter row, okay? Row 1, so row 1 right here, row 1 right here, row 1 right here, and right here, okay? Yeah, so that should be clear now. Shall we move on? Yeah, let's move on. So the next concept I like to mention is frequency response, okay? So just kind of to summarize this lecture, the context, let's think about the context again. The context is that we have a system that we know is linear and time invariant. It's an LTI system, linear and time invariant, which receives an input x of n and produces an output y of n. Okay? And we know that y of n is x of n convolved with h of n, where h of n is the impulse response. Right? Okay, so for any such LTI system, then given the impulse response, we can define the Z transform, right? But it turns out that if we attempt to evaluate the Z transform on the unit circle, that is to say, if we, when I say unit circle, that means the circle of radius 1, okay? So this is to say, on the Z-plane with real part and imagined part, there's a circle with radius 1. There's this circle with radius 1, okay? So with radius 1, if the angle is omega, then this point is e to the j omega, right? This is a circle of radius 1, 半径为1的圆. And this circle is called the unit circle. Z equals to 1, the point set where Z equals to 1. I mean, the absolute value. The absolute value of Z equals to 1. This circle is called the unit circle. The unit circle. And here we're just saying that you should pay attention. This is true. Note that, okay? We often say note that. Be aware. Look at that, okay? Note that. Look at that. When we evaluate Z transform on the unit circle, then what we get automatically is the DTFT. So this is an important matter of fact, okay? Z transform evaluated on the unit circle is the DTFT. DTFT is nothing but Z transform evaluated on the unit circle with Z equals to, when Z equals to EJ omega. Is that clear? If you think just as a reference, note that, okay? note that, recall that DTFT. In DTFT, we have h of ej omega is defined as what? Defined as an inner product of xn e to the minus ej omega and sum over all n. And this is exactly summation x of n e to the minus e to the j omega. E to the j omega minus n right there. And that's exactly x of z when evaluated on right at e to the j omega, right on the unit circle. If the summation converges, okay? So same idea. You can write down all these equality if the summation converges. If the summation converges. In other words, h of z, the z transform when evaluated on the unit circle, is equal to DTFT if the region of convergence contains the unit circle. Let's say again, okay? We say that DTFT is well defined if the summation converges, right? In other words, DTFT is z transform evaluated on the unit circle if the region of convergence includes the unit circle. Okay? In other words, if we often say ROC, okay? ROC means region of convergence, okay? Includes the unit circle. Okay? So that's kind of to be rigorous. We can talk about the Fourier transform of our impulse response. Okay? Now we have when the region of convergence of that includes the unit circle, then the impulse response has a DTFT, because the summation converges. Okay? And the Fourier transform of the impulse response, if it exists, is often called the frequency response. Okay? The frequency response of a system. Right? So if the summation converges, if the summation that is if the DTFT of our impulse response converges, then we call h of ej omega the frequency response of the system. We call it the frequency response of the system H. In what sense? Frequency response. In the sense that now the output spectrum equals to the input spectrum times the frequency response. In that, now our output spectrum will equal to x times the frequency response. The frequency response function. Okay, and we can talk about the magnitude response. If you take the absolute value, then this is the magnitude response. And we just consider angle of the frequency response, then this is called the phase response. As functions of frequency. Okay? For every frequency, we can calculate the gain, the magnitude response, and the phase shift. That's what the phase response is telling us. Right? Okay, so that much about the linear and time invariant system is impulse response, Z transform, and frequency response. Okay, so in the next lecture that we're going to switch to our next lecture, we will introduce difference equations as probably the most important case of linear and time invariant systems. Okay, we'll introduce the difference equation next. 可以吗？要，好，要。Okay, so are we ready to switch? Yeah, can we switch? Any mistake I'm making? Yeah, please. Feel free to interrupt me. Okay, if I make any simple mistake, let me know. Right? Yeah. But otherwise, let's switch to our next lecture. Our next lecture has a title of Linear Difference Equations. And here I want to emphasize on causality. Causality. We're interested in only in the kind of system that we can implement. I mean, time happens in time, okay? Time has a direction, right? Time can never go backward, okay? And we'll see that, at least in my classroom in this semester, I emphasize on using difference equation and implement it so that we have a causal system. Receiving input, producing output, and time goes forward, not backward. It will be clearer when we come to mathematical definitions. But for now, let's just review that linear time invariant system. Let's begin with the kind of recap. Linear time invariant system is characterized by its impulse response, in that the output is equal to the input convolved with the impulse response. And here's an overview. So in the contents right here, and probably into the next lecture, we are going to be covering textbook chapter 5. Okay, chapter 5. Chapter 5 is all about difference equations. And let's have an overview. So first, we will be using this kind of equation. Okay, let's call it equation 1. Equation 1. Okay, yeah. So equation 1, we see that on the left-hand side, we have the output, a linear combination of output samples. Going from the most present sample k equal to 0 corresponds to the most present, the present sample is y of n. But here we are looking back by m more samples, okay, and produce a linear combination. So we're linearly combining the present sample and m up to m past samples, 过去的 sample, right? Current sample, 现在 sample, past sample, 过去的 sample, right? So we make a linear combination of current and past of the output and force it equal to a linear combination of up to n samples of input to the past. Okay? Linear combination here, linear combination right there. Okay? This is the kind of a general form of constant coefficient linear difference equation. Let me say that again. Constant coefficient, constant or linear constant coefficient difference equation. This equation is linear, okay? And this equation is has constant coefficients in that AK and BK, all the A and B coefficients are constant, okay? So let me emphasize on that. So here, these coefficients are constant. They don't change in time, in principle, and these are constant. When they're constant, then we have nothing too much to worry about. The system is still being changing, right? Constant coefficient A and K, A and B's, and it's a difference equation. It's called a difference equation, and in Chinese, it's called 差分 function. It's called 差分 function. So here, the general question in chapter 5 is that given the coefficients, given AN and BN, where n is a dummy variable, okay, from 0 to big N, okay? Given the coefficients, given these constants, everything is constant right here. First goal, can we calculate the first goal is, can we calculate the impulse response given the coefficients? This is like solving differential equation, 微分方程 Kind of the counterpart for continuous time is differential equation. Given constant coefficients, can we solve the impulse response in time, in continuous time? So here we have a fairly similar situation. Given the coefficients that are constants, can we calculate the impulse response? How do we do that? Okay. And secondly, how do we know the frequency response exists? Okay, given the coefficients. How do we know the impulse response has a Fourier transform? And this is a question we need to address. Okay? We need to address. And we will come to that. It turns out that we need to calculate a thing that is called the pose. The pose. Okay? Now we'll come back to that. Turns out that the answer pose need to be inside the unit circle. Inside the unit circle. Okay, that's the kind of take-home message, the outcome. I think we do have time to reach this conclusion, to reach that conclusion today. Okay, but yeah, so these are general questions you should have in mind. How do we calculate the impulse response? And after we calculate, or before we even calculate impulse response, can we predict whether or not the impulse response has a Fourier transform? Okay, and the tools for analysis turns out is the Z transform. Okay, so we'll be using the Z transform a lot. The tool for our analysis is the Z transform, or the Z transform in the UK or India. Okay, in America they say Z, XYZ, but elsewhere people say XYZ, okay, Z transform. You want to sound British, Z transform. Right. I'm not good at British accent, but I know I have a Taiwanese accent. Right, it's fine. Right. And so here is the next point I want to make. Let's come back to h of z. It turns out that when we have equation 1, when we look at that difference equation, it's fairly easy to write down the z transform of our impulse response. And we are going to call that, not surprisingly, we call it h of z, because it's a z transform of our impulse response, h of n. Small h in time, big H in the transform domain. Okay, we use this notation. Turns out that for any difference equation, like in equation 1, h of z can be written in this very useful form, b of z divided by a of z. This is super important, okay, for difference equations only. Okay. Once we concentrate on difference equations, then we can we can write h of z as b divided by a, where b and a are both polynomials. 多项式, polynomials. Where b and a are both polynomials, b of z and a of z are polynomials. 多项式, for the difference equations that we are going to encounter throughout the semester. Okay, so different equations are nice things because they're system function. This h of z is called a system function, which can be written as b of z divided by a of z. And further, if they are polynomials, 多项式, right? b of z and a of z. So polynomials must have roots. 根嘛, 根与多项式. Polynomials must all of them have roots, right? So the roots of a of z and b of z actually have nice names. They're called zeros and poles, respectively. Okay? Yeah. They're called zeros and poles, respectively, when we find the roots of A of z and B of z. I'm sorry, A should be poles. Now, let me erase. The roots for A of z, because it shows up at the bottom, is a denominator. So the roots to the denominator is called the poles. Now, poles and zeros, respectively. Okay, let's make that correction. Okay, poles and zeros. And we'll see in some example, probably not today, but knowing the location of poles and zeros, so there are roots to polynomials, so they occur. They can locate them on the complex plane. And their location matters a lot. Their location actually tells you the frequency response. Okay? They affect the location of zeros and poles, affect the frequency response if the frequency response exists. Right? So the location are pretty important. And it turns out that also the location of the poles determines the stability of the system by the locations of poles. By the locations of the poles. So we'll address these, but this is just an overview of the entire chapter. Okay? So we have several different topics. Okay. Any comments so far? This is just an overview. Okay, just an overview. All right. So if you don't completely understand it, it's fine. We're going to go through them one after the other, one after another, right? So now let's move on to the first thing. Now we can so here we are going to officially introduce systems described by linear constant coefficient difference equations, okay, which is this equation. Equation 1, okay? Call it equation 1. So let's first suggest that without loss of generality, this is a very convenient term, without loss of generality, 在不影响通用性的原则之下, without loss of generality. Without loss of generality, actually we can assume A0 to be 1. Normalize the first factor, A0 here, okay? Without loss of generality. Because if it is not 1, then just divide everything by A0. So it becomes 1. Is that clear? Even if A0 is not 1, then sure, just divide everything, all the coefficients by A0. It's still the same equation. Normalize the equation so that we suggest A0 is 1, and there's an advantage of doing this. If we assume that without loss of generality, A0 is equal to 1, then y of n, we can keep y of n on one side of the equation and move everything to the right-hand side, okay? So let's try to keep yn right here, but move everything to the right-hand side. So now, on the right-hand side, of course, we still have the bn, the b coefficients, which operate on the input. And now we have minus sign. Now k goes from 1 to m. AK operating on the past output samples. Okay? So note that this part corresponding to a linear combination of past output samples. And this is important, okay? I want to invite you to take a closer look to this after we move everything else to the right-hand side, okay? After this move. Why do I think this is an important way of writing the equation? Why? Because now every sample can be computed. Now every sample can be computed by calculating a difference between the first sum. The first sum is just a linear combination of the input and up to n past samples of the input. Past, right? We don't look into the future. There's no need to look into the future. That's my point, okay? And same thing here, subtracted by a summation here, we only look at the linear combination of samples to the past that we already computed. So it's like for any new time when the sampling period, when we increase by one sampling period and we need to compute the next sample. The way of calculating the next sample, the current sample, depends on only things that happen currently or in the past. Nothing needs to depend on the future. So this system can be implemented, let's say by a for loop, by a while loop. This system can be implemented using any CPU, using any computation resource you have. Because now time goes forward. Okay, we don't need to refer. There's no need to wait until the future in order to calculate the present sample. So that's why we like this expression. Okay, by assuming without loss of generality, by assuming A0 is 1, then let me make a suggestion that we move everything else to the right-hand side. So all of a sudden, we have a nice expression in which we express the current sample as a linear combination on the right-hand side, and there's no need to refer to the future. This is good. Okay? So this property is also called causality. Causality. The output only does not depend on the future. Okay, causality. The output, the property that roughly speaking, causality means the property so that the output y of n never, or should I say, does not depend on future samples such as yn plus 1, yn plus 2, and so on, and neither does it depend on the future input samples, and so on. Okay, the output depends on what happens currently and what has happened in the past. This is called causality, 因果性. There's a cause, there's an effect. Effect is caused by something that happened in the past, okay, or presently. Causality. Okay, so far so good. Causal system. So a difference equation. So the message here is that when we have equation 1, then automatically I invite you to immediately think of the equation as if it defines a causal system in this way. Any difference equation you write down, it defines a causal system. And we can compute the output sequentially. For every new input new sample of input we receive, we can produce one sample output. They can be computed. Okay? They can be calculated. Right. So next thing, I would like to show you that h of z can be written as b of z divided by a of z. Okay. So to go through this derivation, so first, let's note that there's a shift theorem which tells us that if x of n has a z transform of big X, then x n minus 1, which is shifting to the right by one sample, okay? Shifting the signal by one sample of delay, okay? By a delay of one sample, then x of n minus 1 corresponds to z inverse xz, okay? So now, let me define a of z as 1 plus a1 z inverse plus a2 z to the minus second power all the way to the last term, that's mth term. Okay, let's define a of z as a polynomial, as this polynomial. And b of z similarly is b0 plus b1 z inverse plus b2 2z to the minus square plus the last term, all the way to the last term, b, big N, z minus big N. Okay, so both of them are polynomials now. Both of them are polynomials like that. Okay. So it turns out that if we take equation 1, right here, and perform Z transform, okay? What happened? It turns out that, I hope it becomes clear to you that on the left-hand side, we have AZ, YZ. And on the right-hand side, we have B of Z, X of Z, because that's the way we define A and B. Because A and B are defined this way. So it turns out that with shift theorem, you can easily show that equation 1 implies this relation, this very nice relation, nice and concise relation, 非常简洁的, very concise relation that A and Y multiplied in the Z domain equals to B and X multiplied in the Z domain. Which is again copied right here, right? Equation 1 implies that AY equals to BX in the Z domain. So therefore, we define the, so therefore let's define H of Z as Y divided by X, and Y divided by X now equals to B divided by A in the Z domain. And we call this the system function. We call H the system function. We call H the system function. And there's a reason why we call it a system function, because the system function is actually no surprise, to no surprise, big H is the Z transform of small h. Okay? Big H is the Z transform of small h. So it turns out that this is the Z transform of small h, which is our impulse response. Why? Because now Y of Z is X. When we define H like that, then YZ equals to X times H in the Z domain, right? So after inverse Z transform, we have Yn equals to the convolution. All right. Okay, so here already we have a lot of information to digest, okay? We have a difference equation, and from there, having a difference equation, we can define two polynomials based on the coefficients. We call the polynomials AZ and B of Z, right? And now A of Z, B of Z divided by A of Z now becomes a function, which is a function of H of Z. And the function of function of Z actually is the Z transform of our impulse response. Okay? So that's a lot of connections right here. A lot of connections right here. You need to kind of digest. But let's look at an example, okay? So before we just, you should go home and seriously think about this. Think through all the definitions. But let's have an example, okay? Let's suppose that you are given a system function. Often it will become clear that in this semester we teach you how to design H of Z. It turns out that we often tells you how to design H of Z. And then when you finally implement your system, you convert it back to a difference equation and compute all the outputs sequentially. 按照顺序来 sequentially. Okay, so this example, of course, is a kind of fake example, but kind of it tells you it gives us a preview what will happen in our design thinking process. Okay, oftentimes in this semester we talk about finding an appropriate h of z in this formulation in terms of a ratio of two polynomials. Okay, so now we have the example of h of z equal to bz divided by a of z. The exercise, in this exercise, I invite you to find the corresponding difference equation. Okay, if you are somehow given the system function, in practice, how do you find the corresponding difference equation so that you can implement with the while loop or for loop, okay, in DSP. Okay, so the question here is find the difference equation corresponding to this system function. Okay, so how do we solve it? How do we solve it? So we need to explicitly write down AZ and B of Z. Okay, so now let me say it's very simple. B of Z is 1 plus Z inverse square, right? So simply, you can work it out, 1 plus 2 Z inverse plus Z to the minus square, right? And similarly, what is A of Z? A of Z is 1 plus 1 half of Z inverse times 1 plus 3/4 of Z inverse, right? Which equals to, it's pretty simple, just need to be careful. 1, yeah, you can work it out. It looks like this 1 plus 1/4 Z inverse minus 3/8 Z to the minus cube, right? Okay, so forgive me if I make a simple mistake right here, but you get the idea. Okay, just expand the product. Okay, just write it down. Write down B of Z and A of Z explicitly, 明显的, explicitly as polynomials. And then what do we have? Then AZ YZ equals to BZ XZ. No, I had either wrong. 好，要小心点啊。B here, A here, right? I was correct? I was correct. Wait. Y divided by X equals to Y A, yeah, so I was correct. Okay. 我故意的啊。No. It's pretty exhausting to be talking about math right after lunch. Not the best time for math. So what do we have? So here, AZ is 1 plus 1/4 Z inverse minus 3/8 Z inverse YZ. So when we just apply inverse Z transform, what we get here is Y of n plus 1/4 of Y of n delayed by one sample. Okay, so that's the trick, delayed by one sample. And this, of course, is to the second power, delayed by two samples, okay? Equals to, similarly, BZ, we have 1 plus 2, no, 1. So let me just jump ahead and directly, now you know that we have X of n, and I'm looking right here. I'm looking at this expression right here, okay? So xn plus 2 times x of n delayed by one sample plus x delayed by two samples, okay? And now, to make the final step, we just move everything except yn to the right-hand side, then we have an implementation, okay? So next thing, I will not write it, I repeat it. Next thing is to move everything else to the right-hand side. Then you have a difference equation which you can implement. You can implement the system and solve the equation computationally in the kind of the order, one sample after another. Okay. So that's a simple kind of exercise. Okay. So. So that's in the next exercise. So in the next exercise, I'd like to show you an example of finding the impulse response given a difference equation. I've been telling you that difference equation gives us a LTI system, right? But if it gives us an LTI system, then when we see the equation, we should be able to calculate. If necessary, we should be able to calculate the impulse response. Because we know the LTI system is characterized by the impulse response, right? So it's important. We want to be able to calculate the impulse response given the difference equation. So how do we do it? So I'm going to show you an example, okay? It turns out that, well, let me mention that the impulse response, again, is defined as the system's response to delta function, okay? When the input is delta function, the output is impulse response. Okay? So now, turns out that we can solve it using the transfer line, which is what I'm going to show you today. But it turns out that we can also find an alternative solution by linear algebra. But we will not be covering that. By linear algebra. Okay? So the example I'm going to use today is this simple equation, a second order. This is a second order difference equation because we look to two samples in the past. Second order difference equation, where each current sample depends on past two samples plus the input. Okay, is that simple? Right? If every current sample is the sum of past two samples plus any input that we might receive at the moment. Okay? So for such kind of system, what is its impulse response? What is h of n? What is h of n? Turns out that it's easier to, if we write down, we work it out in the z domain, okay? It's easier in the z domain, so that's what I'm going to do next, right? So to work in the z domain, first, let's write down b of z and a of z, okay? So here, a of z, what is a of z? A of z corresponds to the y term, right? So it's 1 minus z inverse minus z to the z inverse square. Okay? And what is b of z? B of z, because here we have only one term. Okay, so b of z is simply 1. So here, quickly, h of z defined as y divided by x equals to b divided by a, which equals to 1 divided by the polynomial 1 minus z inverse minus z inverse square. Okay? And from here, this next step is the key step. Okay? This is a key step. We want to make this decomposition or factorization. Okay? It turns out that when we have a polynomial here, we need to find the roots. D1, D2 is the roots. We need to find the roots to a of z. Okay? So quickly, I should tell you an intermediate step. The intermediate step is that a of z can always be factorized as the product of like that. 1 minus d1, z inverse. 1 minus d2, z inverse. This is a fundamental theorem of algebra, 代数的基本原理, fundamental theorem of algebra. Any nth order polynomial has n roots on the complex plane. Okay? So you can always factorize a polynomial. In this case, we have a second order polynomial. It has 2 roots. And so just it's a bit tricky that here we write down, this polynomial z inverse. But anyway, so D1 and here D1 and D2 are roots of A of Z. Or they are also called poles of the system. Okay? Now, we find the poles of the system. Okay. And then further, the next step, from this intermediate step, which can always be done, right? You can further, it's preferred, I recommend that we further decompose the product into sums like that. And where we need to also determine the coefficients alpha 1 and alpha 2 on top, okay? And there are a few ways of determining alpha 1 and alpha 2. But first of all, D1 and D2 can be just solving a quadratic the equation, right? So D1 and D2 is, I'm pretty sure that most of you know the formula, you learned in high school. D1 and D2 is 2A 分之负 b 加减 b 平方减 c 更好, right? Is 2 times 1 plus or minus b squared plus 4 times 1 times 1. D1 and D2. Let me erase this. So it turns out that D1 and D2 equals to 1 plus or minus that divided by 2, and the result is 1 plus or minus square root of 5. Okay, that's D1 and D2. And I'll leave it to you. So there are such you can probably, it's pretty straightforward also to figure out the coefficient alpha 1 and alpha 2. Okay, I wrote it down somewhere. I did my homework. I'm not just going to copy the result to you. The alpha 1 and alpha 2 equals to 2 square root of 5, 1. It's not the most interesting exercise, so I'll just write it down for you. And 1, there's a minus sign, okay? Yeah, something like that. But in principle, you can find it, okay? In principle, after we reach this expression u, and we know that D1, D2 for sure are the two roots, there will be no other trick. D1, D2 for sure are the two roots like that. So after finding D1, D2, you can find out alpha 1, alpha 2. There are at least two different ways. Okay? I'll leave it to you. It's pretty straightforward. You can find alpha 1, alpha 2. You can solve that. Okay. So once we have the expression, okay, once now we have the expression that we know that we can find all the coefficients right here, then this is our system function, an expression of our system function. An expression of our system function. And our goal, remember our goal, what is our goal? Our goal is to find the impulse response, right? And the impulse response is the inverse Z transform to big H. So we somehow need to go from this domain from this equation back to this expression back to the time domain. We need to somehow go back to the time domain. And it turns out that as an exercise, let me just jump ahead and say, we have two terms right here. One is alpha 1, right? Alpha 1 divided by 1 minus D1 Z inverse plus alpha 2 divided by 1 minus D2 Z inverse. Okay? It turns out that we can attempt to rewrite the expression as sum of two geometric series. Geometric series, 几何级数, geometric series. How do we do that? You'll know what I'm doing immediately. So here, this is alpha 1 times 1 plus D1 Z inverse plus D2, not D2, D1 square. D1 square Z minus second power, D1 to the third power minus z to the minus third power and so on. This is a geometric series I want you to notice. 它是一个几何级数一个等比级数So that's kind of applying the formula in a backward way. Because in high school, we all learned that the summation of this geometric series has this expression, right? In high school, we know that this summation of this geometric series has this expression if the common ratio is inside the unit circle, right? If the common ratio does not exceed 1, right? If the common ratio, 公比common ratio, if d1z inverse is smaller than 1, then the two expressions are equal, okay? And similarly, for the second term, we have alpha 2, 1 plus d2 z inverse, d2 square, z minus square, let me write one more term, d2 to the third power, z inverse cube, and so on. Again, this is the kind of reverse way of expressing the geometric series, okay? The two are equal, and this equality holds if the common ratio d2z inverse absolute value is smaller than 1, okay? So that's kind of rewriting our Z transform in terms of geometric series. And the equality holds if two conditions are valid. If this is true and that is also true, then we can write down the equality rigorously, and this is rigorous. Okay? But next, what is h of z? Actually, by definition, is that, right? H of z relates to the impulse response by definition in this expression. This is how Z transform is originally defined, right? But now, so on one hand, we have this equality. On the other hand, we have the equality by definition. Okay, and it turns out that any power series can have only, any function can have only one Taylor series expansion. Okay, this is about the uniqueness of Taylor series expansion. 泰勒展开Any complex value function can have only one unique Taylor series expansion around z equals to 0. Okay, so therefore, when we have two expressions that are equal, it turns out every term should be equal. Every term has to be equal. Okay, so this implies that h of n for every n here. Let me just, sorry for the delay, so I want to finish right here. It means that h of 0 is equal to alpha 1 plus alpha 2. And her h of 1 is equal to the sum of coefficients to the z inverse term. Okay? So h1 is equal to alpha 1 d1 plus alpha 2 d2. And so I want to write down one more term before we conclude. h2 is equal to alpha 1 what? d1 squared plus alpha 2 d2 squared, just by comparison of coefficients, 比较系数法 By comparison of coefficients, we figure out, well, every coefficient should be, the equality should hold for every term. Therefore, h2, when we continue, h2 is alpha 1 d1 squared, alpha 2 d2 squared, and so on. So every k, h of k should have this general expression. Alpha 1 d1 to the kth power plus alpha 2 d2 to the kth power. So if we plug in numbers, where do we have the numbers? The numbers, plug in the numbers 2 square root 5, 1 plus square root of 5, what? 1 half of 1 plus square root of 5 to the kth power plus, that's a general expression of our impulse response for any k greater than or equal to 0. Okay, so I need to end my lecture right here. Okay, so here is an example of finding the impulse response of that difference equation. Okay, so hopefully with this example, I think we are ready for tomorrow's follow-up discussion. Okay. In tomorrow's follow-up discussion, it will be all about, we have I made 3 simple exercises for you about the difference equations, how to find their impulse responses, how to calculate the frequency response, and so on, right? So hopefully when you go home, if you have some extra time to work, please work on the follow-up discussion. And we'll come back for that, okay? Right. Thank you for being here, and thank the people on video streaming. I thank the classmates on in the other classroom. So that's it for today. Thank you. What?
因为他们今天不是去，他们今天不去手册嘛，然后你们是说跟就带实验室的人下去这样 PPA。
哦，这样子啊。